Frontier AI training costs now center on the final commitment rather than the hyperparameter search. Powering up a full-scale pre-training run requires committing tens of millions of dollars and months of cluster time to a single configuration. To navigate that risk, researchers are staking entire compute clusters on a simple two-parameter mathematical line fit to determine their learning rate. This equation is calculated using proxy models running at merely a quarter of the target model's width on a fraction of the total token budget. This creates an absolute threshold. You place your bet on a predicted hyperparameter, and the only way to find out if the math held up is to spend the compute and run the model to completion. At the frontier scale, predicting the learning rate transforms into an unhedged, unfalsifiable leap of faith. Calculating that leap of faith requires chaining together two distinct transfer mechanisms. The first tackles the physics of model width. On the horizontal axis, we track model width. Researchers apply a MUP adaptation tailored for mixture of experts, targeting architectures utilizing multi-head latent attention and the muon optimizer. The intended result is scale invariance. The optimal learning rate remains perfectly flat as model width expands. Achieving this stability requires a precise mathematical adjustment. The muon optimizer's learning rate must be scaled by 0.2 times the square root of the maximum of dimensions A and B, relative to a standard atom W baseline. But this exposes a limitation. MUP is strictly a width result. It indicates the optimum does not move as you widen the model, but says nothing about training dynamics over longer time horizons. Assuming a MUP transferred learning rate is horizon independent leads to inefficiency. If you ignore the time dimension, you leave significant loss on the table at long training budgets. This brings us to a critical admission in the recent literature. The optimum learning rate fluctuates as the token budget grows. Adding a vertical axis for the token budget in log-log space reveals the optimal learning rate decays predictably as token count increases. To chart this, researchers built a proxy model with 3.3 billion active parameters, precisely a 1/4 width scale of their final target. They ran this proxy out to roughly 500 billion tokens, mapping the downward trajectory of the optimal learning rate. However, hidden inside this data collection phase is a significant structural fragility regarding the batch size schedule. During the run, the researchers raised the batch size from 8 million to 32 million tokens, specifically after crossing the 200 billion token mark. That shift disturbed the training dynamics. As a direct consequence, the researchers had to discard every single fit point generated before 255 billion tokens to maintain the regression's accuracy. If you want the next technical breakdown the day it lands, subscribe. The resulting mathematical fit is conditional on that specific batch ramp. Changing the schedule, by altering the ramp point or using a constant size, invalidates the paper's intercept and requires a complete refit. By isolating only the stable data points collected after 255 billion tokens, the team built a linear regression to calculate their final target. This requires a 20-fold extrapolation. The line is drawn through a tiny cluster of proxy observations, then extended far outward across the empty graph to a 10 trillion token horizon. On the measured token leg, this extrapolation fit reaches an R-squared of 0.95. At the end of that mathematical tether lies a single precise prediction, an optimal learning rate of 3.85 times 10 to the negative 4. The researchers made their final commitment. They used this exact hyperparameter to pre-train their final model from scratch. The resulting architecture was a 155 billion parameter mixture of experts model, holding 17 billion active parameters during any given forward pass. The entire compute budget was staked on this single run, without conducting a single learning rate sweep at the 155 billion parameter scale. The model finished training, shifting the focus from how the learning rate was predicted to how the researchers validate that the final result was a success. Here, we hit the epistemological limit of the methodology. The headline validation for this transfer framework is based on an n=1 run. The primary evidence for success is the training trajectory. Plotted on a graph, the predicted learning rate traces a clean loss curve, free of spikes. But smooth curves can be deceptive, routinely conflated with optimality. In reality, suboptimal parameters look identical on a graph. A learning rate exactly half of the ideal value will also produce a completely smooth curve. It simply converges to a worse final model. At extreme scale, training stability represents a performance floor, whereas optimality remains unproven. No amount of staring at a single, isolated loss curve can definitively prove that loss wasn't left on the table. This creates a structural paradox. The only experiment that could successfully separate an optimal rate from a merely survivable rate is a second full-scale run at a different learning rate. The authors themselves are direct about this limitation, admitting in the paper that conducting exhaustive full-scale sweeps to definitively verify the optimality of their predicted learning rate is computationally infeasible. At frontier scale, this methodology is structurally circular. The exact sweep needed to prove the transfer definitively works is the exact sweep the method was invented to avoid.